All right. Hello, world. Testing. 1, 2, 3. Can you hear me OK? Well, good to see everyone waving. So this is our third lecture on cybersecurity. Today we're going to focus on networks and systems and how you keep those secure. We're then going to take next week off, and then in 2 weeks. Sorry. Is that Carter? OK. And then we're going to take next week off. And then in 2 weeks' time, we'll wrap up the class with 2 more lectures to which you'll be invited. We'll send an email reminder. Let's go ahead and dive right into our usual. You're going to be invited to say hello, world. Turn on your cameras if you would like to participate in this here souvenir photo. Feel free to smile, wave, look serious. And our friend Rong Shin is going to start screenshotting.
Oh.
Hello, world.
Everybody.
Привет.
How you all doing?
All right.
Nice.
All right. That was great. It's funny how you can barely make out anyone, but there was a perfect hello, everybody, which made its way through, at least on our speakers here. We're going to begin in just a couple of minutes. Let me see if there's any questions. If Rong Shin, we could pin 1 or 2 folks. If you have any questions about what we've done thus far or where we're going with the class, feel free to raise a virtual Zoom hand before we begin here. Let's see. How about over to Ali?
Who know public key about public and private, and who know the ciphertext? How can are there an example? How can not convert ciphertext to plain text with public key, which is cipher that plain text?
Yeah, I had a little trouble hearing you, Max. Can we increase the volume out here? If your question is about how public and private keys can be used for encryption, in general, the process is if you, Ali, have a public and private key, you, of course, keep the private key private. You never give it to anyone. But you have a public key that you can post online in your emails, on your website, in your social media profiles. And if I, David, download your public key or copy-paste it, I can then use that key to encrypt information that I want to then send to you. And mathematically, only your private key should be able to decrypt that same information, if I answered that correctly. All right, thanks for that question. How about over to Alex? Carter, we're just doing a couple questions. And Max, sorry, Alex, go ahead.
Do you hear me? Sorry.
Yes.
Yeah, you can speak to Carter first.
Oh, go to you. Your turn,
Okay.
Alex.
Okay, so my question is more general. Where are you going with this course? So will it go deep? Will it have some practical exercises maybe? So scratch on that surface down the line on October probably, but maybe you can give an outlook of the course. And if it's not going too deep, do you plan another course which will go deeper?
OK, good questions. So today we will focus on how you might secure systems that are interconnected. Next, in 2 weeks' time, we'll then focus on securing software that you write or that you use. And then lastly, we'll focus on issues of privacy. Per the course's description, we will try to cater to non-technical and technical audiences alike. And what we mean by that is that the course is meant to be technical. It's meant to have foundations in computer science formally. So it won't be surface level. But we won't assume that you've taken computer science before or that you know how to program. And so today, for instance, will be another good example where we'll give you a little bit of a taste of like what HTML is, what HTTP is, so that you have a mental model with which to understand some of today's actual cybersecurity topics. In the course's assignments, which will be available in October and beyond, there will be opportunities not only to review that kind of material, but likely to do hands-on things as well. We're going to do our best to come up with exercises that work on people's Macs and PCs and more generally on different systems. But that's what we're going to be working on over the next few months as well. All right. Well, we are just about ready to go here. Let me go ahead and reset here. And then in just a moment, we will begin today's lecture on cybersecurity. Thank you for joining us again. All right, this is CS50's Introduction to Cybersecurity. My name is David Malan, and this week let's focus on securing systems, particularly those that are somehow networked or even internetworked as well. Now, recall from last time that we presented encryption is really the solution to a lot of our problems, and that's going to be a building block that we continue to use to solve a lot of our concerns around the security of not only our accounts, our data, but now also our systems. For instance, let's consider something that you yourself are perhaps using right now, which is Wi-Fi, somehow connected via wireless technology to the internet and beyond. So probably by now you realize that when you're on Wi-Fi, you have to first choose your network. And you might choose your network from a drop-down menu on your computer or the like, or it might auto-select it. But there's at least two types of networks. One that are unsecured, and then two which are secured in some way. And odds are you recognize, and you've already been taught through practice to recognize the little padlock icon on your phone or laptop or desktop as signifying that your Wi-Fi connection is indeed encrypted. Now, what does that actually mean? Well, in particular, in this context, it would mean that any of the traffic, any of the internet packets of information, so to speak, like envelopes of information going from your device off onto the internet, are somehow encrypted, at least encrypted until they reach whatever device your device is talking to wirelessly. So you have a encrypted connection between that wireless device, often called an access point. Now, what is the actual technology that's being used to secure Wi-Fi networks nowadays? Well, hopefully you're using among the latest versions of this, Wi-Fi Protected Access, or WPA. And this has evolved over the years, and there have been a few different versions. And so in general, whenever you configure a phone or whenever you configure a laptop or desktop, ideally you're connecting to a device nowadays that supports this technology and the latest version thereof. And in a nutshell, what that ensures is that indeed your traffic from your phone, laptop, or desktop is somehow scrambled between you and that other device. And that device, in turn, is probably connected to devices called routers, computers that route left, right, up, and down information on the internet, which might then connect to other routers until it finally reaches its destination. So for our purposes, though, Wi-Fi protected access and using a secure Wi-Fi network is only technically encrypting your traffic between you and whatever device is maybe on the wall, on the ceiling, nearby, the little thing with antennas, perhaps, that you yourself are actually talking to. So why do we care about this? Why do you want even your Wi-Fi connection, for instance, to be encrypted? Well, it turns out a lot of what you and I do on the internet isn't necessarily encrypted already for us. Now, fortunately, this is decreasingly the case. The world has gotten better about using more and more encryption in various products and software and applications that you and I use, but not necessarily, because odds are even some of you are probably in the habit of typing http://www.example.com or whatever domain you're actually trying to visit. Now, maybe you don't type even that, but you're certainly familiar with this prefix, this acronym HTTP, which stands for Hypertext Transfer Protocol, which is a fancy way of saying that this is a protocol, a language that computers use when talking on the World Wide Web, or web for short. So what do we mean by that? Well, if you're sitting down at a browser on your phone or laptop or desktop, and you're visiting a URL that starts with HTTP, your device is about to communicate with some remote server using this protocol, this language, really a set of conventions for talking between each other. But the catch is, per last week when we focused on the security of our data, the information or the packets of information that we're sending from browser to server and back are vulnerable to eavesdropping potentially if you're only using HTTP. Well, why is that? Well, HTTP by definition is not encrypted. It's just text messages, often English-like in nature, but they're not at all scrambled, which means if Alice is sitting at her desktop or laptop or phone and trying to visit some website, here represented as our friend Bob, there could be some third party, Eve, who's eavesdropping in between, a machine in the middle, so to speak, that could be looking at every request Alice is making and every response that Bob is sending, if again, Alice is the user in the story and Bob is the web server in this story. So you're vulnerable if you're only using HTTP and certain other protocols or technologies to these machine-in-the-middle attacks. And the attack in this case might just be someone nosily trying to know what it is you are doing on the internet. But worse, they can even manipulate what you're sending or receiving if these systems are not using some form of encryption. So let's take a specific example. When you visit a website on the internet, you are downloading effectively a language called HTML, Hypertext Markup Language. If you take a course like CS50 itself or an introduction to web development, you'll actually learn a language that looks a little something like this. And I've shown only the highlights using ellipses here, ... to wave my hands at details that won't matter. But this is the kind of text or language that we get back from a server when you visit something like http://www.example.com. But notice that this doesn't seem to be scrambled. Even though it might look cryptic to you if you've never written or seen HTML before, it doesn't look like random zeros and ones, certainly. It looks pretty intelligible. And in fact, it looks somewhat English-like with words like body here. Well, the catch is, if this is the response coming back from a web server to a web browser, for instance, Alice's own, what could happen is that some eavesdropper, some machine in the middle, could actually inject additional HTML code into the web pages that you and I and Alice are downloading. Now, what is this representative of? Well, this is another feature you might learn in a course on website development. But let me highlight just one key phrase here, because this is a common use case. It is possible, therefore, for a machine in the middle to inject something like advertisements, or worse, something actually malicious that tries to steal your data in some way. But a common scenario for this machine-in-the-middle attack is when your internet service provider, or the coffee shop whose Wi-Fi you're using, or the hotel whose Wi-Fi you're using, wants to inject advertisements into maybe each and every web page you are visiting, even if those web pages weren't even designed to have advertisements. These things might be prepended to the very top of the page, for instance. Now, the reason that machines in the middle are able to do this, though, is simply because if you're not using encryption and Alice and Bob are communicating insecurely in that sense, well, there's no telling what they could add to the responses that are coming back from this web server. Let me pause here before we move on to yet other threats to see if there are now any questions on this particular attack. Yeah, Matthew? You seem to be unmuted, but can you hear us, Matthew?
Hello, sir.
Yes, now we can.
Ask you questions.
Sure.
How can I know the HTTPS website is safe or not? Because someone can inject me a machine in the middle attack, right? How can I know it is safe?
A good question, and that's what today will be entirely about. For now, we're only talking about HTTP. HTTPS is going to somewhat secure things for us, but stay tuned for some threats that we'll still be vulnerable to. Other questions that we can call on here? How about Hameen, if I'm saying it right?
Yes, sir. I want to know how to detect machine in the middle and get rid of it. How to detect machine in the middle and get rid of it?
A really good question. So how can you detect a machine in the middle and get rid of it? That certainly should be a worthy goal. Short answer is you cannot necessarily detect it. It is possible that a machine in the middle can be doing all of this without your own knowledge. How do you get rid of it? Well, that too is going to be the focus of today. Namely, encryption is going to help us push back on exactly this threat. In fact, let's go there. How might we now start to defend against? Well, let me fix that here. So we'll focus on defending against that threat. But first, let's consider some additional threats or concerns that we might have. And one of them technically is called packet sniffing. So again, a packet is a virtual envelope of sorts that you might use when sending data on the internet. And so in fact, here is a pretty standard envelope in which in the human world, I might put a letter and then write something on the outside and send it off to someone through the mail system. Well, you can think of packets in the context of computer systems as being analogous to this, whereby this is an envelope whose purpose in life is to get data data from one point A to another point B, so from Alice to Bob. And inside of this packet is the actual message that Alice is sending to Bob, and Bob is hopefully sending back to Alice. So it might not all fit in one packet. So indeed, the internet tends to use multiple packets like these. But that's an appropriate metaphor to think about what it is we're doing here, otherwise digitally. So packet sniffing, then, is kind of like trying to get a sense of what's going on inside of these envelopes. And indeed, if the contents of these envelopes are not encrypted, scrambled securely in some way, well, then any machine in the middle can technically take a quick glance inside of these envelopes, so to speak, see what's inside of them, even change what's inside of them, as we've seen, and then pass it along. So what are the implications for what this makes possible, therefore, if you are vulnerable to packet sniffing by, again, not having your systems use encryption when they are talking to one another? Well, here, for instance, is one example of what could be inside, metaphorically, an envelope like that. This is the kind of message, written mostly in English, that represents a browser requesting a web page from a server. In particular, when you visit a search engine, for instance, and type into the search box what it is you're searching for, maybe you're searching for cats, what happens is your phone or your laptop or your desktop creates a virtual envelope like that, opens it up, puts inside of it a message that looks like this, closes the envelope, and then sends the envelope off onto the internet to a web server that conversely is going to open the envelope, read this message, and hopefully send you back a whole bunch of search results about cats. Now, most of this is arcane detail that we don't particularly care about, including where it is we're visiting for this story. I'm using example.com as just something generic, but you could imagine it being Google or Bing or the like. Here you have a command get, which means literally get me a web page. /search is implying that I'm searching for something. But here's the interesting part. What I'm searching for is a query for cats, where a query is a question or a search request of yours, and cats, of course, is what I'm searching for. So this is to say, inside of this envelope, whether you're searching for cats or dogs or anything else, there is some mention of that search query inside of the message, inside of that envelope that's being sent from Alice to Bob, or from you to Google or Bing. Lastly, there's this mention here, which is referring to exactly the same protocol, HTTP, in this case, perhaps version 3. But ultimately, it's the yellow highlighted text here, that mention of cats, that's worrisome if some machine in the middle, some adversary, can sniff this packet and see what's going on inside. Now, there's other threats similar in spirit. When you request pages on the internet, you don't sometimes just search for information like cats, which I don't really care about if people know, since everyone else on the internet is searching for cats. But what if I'm trying to check out on some website like Amazon and buy something with a credit card? Well, then what is inside of this envelope is some text that looks fairly similar. We still have a host in this story of example.com. I'm still using HTTP. I'm not getting information per se. I'm posting information akin to uploading my credit card to the server. And in particular, down here is a representative of how my credit card might be stored inside of this virtual envelope. And if I highlight that, indeed, you'll see a credit card number that hopefully doesn't actually work, but it is the right length. If anyone sniffs this packet, they might actually be able to find my credit card and maybe my name and my address and the little code that you need and more with respect to whatever it is I'm checking out for. So it's that easy if the data is itself not encrypted. Let me pause here then too and see if there are any questions. Yeah, let's go over to Ankiomabam. I'm sorry if I'm saying that wrong.
Hello, sir. Yeah, I wanted to know if someone is performing an attack, right, from a machine in the middle, does the person actually have to be connected to the same Wi-Fi network as you, or they could be on a whole other network?
A really good question. So in general, they would be connected to the same Wi-Fi network so that they are generally, they would be connected to the same Wi-Fi network, but even that is not necessary. So long as they are within reasonable proximity to you and their laptop or their device has an antenna that can receive all of the wireless packets that are around you, they don't necessarily have to have access to that same network, especially if it's unencrypted. And in fact, there exists software that can listen to all possible networks that are around you. And so that, too, is a potential threat. Other questions on this here? Yeah, over to Mahal?
So my question is, do people have to know your IP address in order to be able to see what you're doing or read what websites you're going to?
A really good question. For those unfamiliar, an IP address is a unique identifier that every computer on the internet has, much like you have a postal address to which humans can send mail. Short answer, Mahal, is no. Like someone does not need to know your IP address in advance for at least these wireless attacks, because they can simply, as per my other response, listen to all of the wireless traffic nearby, and they can actually see the IP addresses of senders and receivers flying by, so to speak, throughout the air. And how about one more question? And Andrew and team, is there anything we can do? OK. Yes, over to Shinaz.
Oh, hello. I just wanted to ask if this no sniff controlled by the HTTP header, no sniff in the HTTP protocol. Yeah, I am correct.
Sorry, it was a little fast. Say it once more.
OK. In the HTTP, there is a header called no sniff. Is this something related to this topic or not?
And let's see. I'm sorry. I had trouble hearing that one, too. Carter, did you catch that? No sniff. Do you mind, Shinaz, do you mind asking your question in the chat just so we can see it better?
OK.
And let me keep an eye on here. And if you don't mind, let's go ahead and take a 5-minute break here just so we can reset. And in 5 minutes, we'll resume on these threats. Let's consider next another. Start that over. OK. Let's consider next another attack that we're vulnerable to by nature of our same browsers using things called cookies. Now, odds are you're generally familiar with cookies, and there are these little files that websites typically put on your browser so that when you visit a website, the website remembers who you are. And that's useful if you've logged in before, you have certain preferences and the like. So in general, cookies are a very useful thing, but you probably also know that they can also be used for malicious purpose too, for tracking purposes as well. And we'll focus on exactly exactly that when we focus on privacy. But for now, let's focus on the security of these cookies in particular, because they actually make us vulnerable to what's called a session hijacking attack. Now, what do we mean by that? Well, if you visit a website like Gmail or Amazon into which you typically log in so that you can access your email or your order history or the like, the website, of course, needs to know and remember who you are so that when you go from email to email or from product to product, you don't have to keep logging in again and again and again. Somehow the browser is remembering that you have already authenticated and therefore who you are. Well, how is that actually achieved technically? Well, it turns out in the context of HTTP, this protocol that web servers and web browsers use, when you log in to Gmail or Amazon or any website that uses sessions, so to speak, to keep track of who you are, they send back a message in one of those virtual envelopes that looks a little something like this. 1, a reminder of what protocol they're speaking. 2, a status code that indicates everything is OK. And in fact, 200 means exactly that. OK, here is a response. And you might actually be familiar with at least one other status code like this. In fact, yep, 404 is a status code that you might see coming out of other virtual envelopes that the world has decided means file not found. But 200 indeed means OK. But notice here, inside of this imaginary envelope is another line of text, namely set-cookie : and then what we'll call in general a key value pair, some piece of data that my browser henceforth will hold on to remind the server who it is. In particular, the key is called session, and the value of that key per the equal sign is 1, 2, 3, 4, A, B, C, D. Now that one's a little silly and a little easy to guess, but imagine that the value of these session keys is typically longer and more random. That is to say, no one should be able to guess it. This one here is just meant to be representative. So what does that actually mean, and how is it actually used? Well, when you log into a website, and you provide your username and password, and you want that website to remember who you are and that you've logged in, essentially a response like this comes back from the server saying, hey, browser, your session key is 1, 2, 3, 4, A, B, C, D. And then, because the browser understands HTTP, this protocol, and therefore adheres to its conventions when talking to web servers, the browser that receives this set cookie message is going to thereafter constantly remind the server what its cookie value is. It's as though the server is stamping my hand with this here smiley face, and every time I go back to the same server when I click on a new email or I click on a new product, I'm representing my hand just like you might at an amusement park or a club or a bar who's already checked your ID or checked your ticket, and they just want a quick and simple way to remember that, OK, yes, we have authenticated you already. So what is actually happening at the browser's end is that when it receives this set cookie message and it is remembering that on the server, remembering that in its memory, subsequently when the browser, messed up. Can I fix one thing? Sorry, y'all. Thought I had one more visual there that I wanted. Can't. Okay. Let me try to fix this then. Okay. Okay. Subsequently, when the browser visits another page on that same server, what it should do in its virtual envelope is include a message like this. So if, sorry, I messed up again. OK. Subsequently, when the web browser visits another page on that same site, what it should send in its own virtual envelope would be a message that looks a little something like this, where it's trying to get some other web page using the same protocol, but instead of saying set cookie, it literally just says cookie colon, and then that same key value pair. And that's akin to the browser reminding the server that its hand has been stamped and what the value of its session key is. And then this key, this 1, 2, 3, 4, ABCD, is used so that the server can check in its memory or check in its database. Oh, wait a minute. What does David have in his shopping cart? Or wait a minute. What emails does David have in his inbox? And therefore, the server knows to show me my inbox or my shopping cart and not yours or someone else's altogether. Now, these cookies, therefore, in principle, are a good thing because they allow servers to maintain state. State is memory of some piece of information. And so the state here might indeed be my inbox or my shopping cart or some other such piece of information on some other website. They can be used maliciously, and they can be used maliciously by these same machines in the middle. For instance, there are what we might call super cookies, which are somehow planted inside of your virtual envelopes without your even knowing, and in a way that you can't necessarily stop yourself because they don't come from your server, because they don't come from your laptop, rather... because they don't come from your browser, they come instead from your internet service provider, for instance. So how might this work? Well, suppose that I'm sitting down at a browser for the very first time and it has no cookies. My hand has not even yet been stamped. And I visit, for instance, example.com. But suppose I'm going through an internet service provider, either a cable modem company, a DSL modem company, a cell phone provider, or the like. And unbeknownst to me, if my traffic is not encrypted, and therefore the contents of these packets are not only sniffable, they are changeable, my internet service provider could actually do something like inject a cookie into my packets on my behalf. So in this case, I'm using, for the sake of discussion, the same sample value as before, session equals 1, 2, 3, ABCD. But in this story, I'm proposing that it was not a server that told my browser to remember that value. Rather, it's my internet service provider injecting this cookie into my traffic when it's between points A and B, thereby serving as a machine in the middle. And why would my internet service provider want to do this? Well, we know from historical cases already it's for tracking purposes. It's for advertising purposes. Why? Because even if you are so vigilant about not keeping cookies in your browser, maybe using private mode or incognito mode or the like, your internet service provider or some machine in the middle can still inject this additional information to effectively track you. Now, how does this work? Well, by nature of your internet service provider in this story, injecting something like this cookie into all of your packets, well, then you will appear to websites as having this session cookie. And those websites then can maybe serve advertisements to you based on that value, or simply keep track that you are this particular customer of an internet service provider. Now, this has happened with a few companies in the United States over time, and thankfully there was enough pushback in the media that you now have the ability, depending on who your provider is, to log into their website, log into your account therein, and opt out of this sort of tracking. But for our purposes today, really the focus is on the relative simplicity with which this kind of attack or this kind of feature can be implemented by machines in the middle when you yourself are not encrypting your traffic, be it in this case wirelessly or via any type of technology like HTTP that by default is in fact not encrypted. So what might the solution here be? Well, as promised, encryption really is the solution to a lot of the world's problems, at least as of now, and therefore to yours too. So you probably already know and have heard over time that you should probably be using HTTPS anyway, where the S represents secure, for exactly these reasons. But now hopefully you have a better sense of what all of these reasons are and have been, because it goes beyond just being able to see the contents of your email or your shopping cart. Even much more can be seen or even changed without your knowing when your data is not encrypted. So when you use https://www.example.com or similar, it's as though Alice and Bob, for instance, Alice and some website, have a secure connection between them, even if there are other devices or companies like routers or access points or internet service providers between them, because so long as Alice and Bob are using a shared secret or perhaps public key cryptography and a public and private key pairs, key respectively, they can communicate securely, thereby ensuring that this virtual envelope that we keep talking about might still have some publicly accessible information on the outside, because the packet still has to get from A to B somehow, but the contents of this virtual envelope now, if using HTTPS, are ideally completely scrambled or encrypted. Now, how is that done? Well, it turns out that there's another protocol in the world that handles precisely that process of encrypting HTTP traffic, aka HTTPS. And the most recent version of this protocol is called TLS, which, funny enough, is perhaps an acronym that many people have still not heard of, but you might have heard of SSL, which is essentially an earlier version of it. But TLS is essentially the new and improved version of SSL and what modern browsers should now be using. What does this do to go about encrypting your traffic? Well, it turns out it relies on our focus from last time of public key cryptography. And this principle that if you give two parties, A and B, each their own public and private key, using that, you can solve that chicken and the egg problem and actually communicate securely, even if in advance you don't have a shared secret. So recall that asymmetric cryptography allows us to establish a secure connection, even if you've never visited some website or some app before now. So what does it mean for a browser to be using TLS and thus HTTPS to communicate securely with a web server? Well, the web server in this story now has what we'll call a certificate, a digital certificate. And you can think of this for now as really a public key that has been signed by someone else. So the website has a public key and a private key, and the private key, as always, stays private. But in this case, the web server has a public key that's also been digitally signed by some third party. And for now, let's assume that there are some big third parties out there, companies really, that we all, or at least the browser manufacturers, the Googles, the Microsofts, the Apples of the world, all trust on our behalf. And they are the ones signing off on the legitimacy of these so-called certificates. Well, these certificates technically are of a type called X.509 if you're curious about the type of protocol being used, but this is just the standard format in which these certificates live. But you can think of a certificate really as almost a printed piece of paper with some interesting information on it, like the name of the website and how long the certificate is valid for, and also the public key, which we said last time is really just a big number that has a mathematical relationship with that private key as well. Now, who are these big players, these big companies that are doing the signing of these website certificates? Well, you might have heard this phrase at some point if you set up your own website, perhaps. These are called certificate authorities, or CAs. And these are a collection of companies and entities whose purpose in life is to digitally sign certificates. And the various browser manufacturers of the world, Apple, Microsoft, Google, Mozilla, and others, have gotten together and included in their browsers, like Edge and Firefox and Safari and Chrome, a list of certificate authorities that they trust. And if the idea is that if you trust Apple and you trust Google and Microsoft and Mozilla and other browser manufacturers, then by transitivity, you should trust any of the certificate authorities that they in turn trust. And this is really just a list. You can think of it as a file or a database that's built into your browser, maybe gets updated over time when you download new versions of your browser, but it has a list of certificate authorities and in turn their public keys that you should be willing to trust. And let me fix that. It has a list of certificate authorities that you, in turn, should trust. So how now does this all work? Well, when you visit a website, or Alice, for instance, visits a website like Bob. Let me fix this. 1 second. So how now does this work? When you visit a website, your browser, all this time, when it's using HTTPS, and therefore, underneath the hood, this protocol called TLS, your browser downloads from that website its certificate, which is to say its public key, as well as, in turn, the signature therein. What does your browser then do? Well, your browser knows how to implement all of those protocols from last week that we discussed, and we can think of them this week as really a black box. This black box implements public key cryptography in some form. So what does your browser do after downloading that certificate? Well, it runs it through some algorithm, some code that comes with the browser, and outputs a hash. And recall that a hash is typically, in this context, just a fixed length message of numbers and letters that just represents more succinctly what its input was, which in this case was a certificate. Meanwhile, what your browser next does is it uses the public key of that website and it decrypts the signature that is on that certificate from that website. And if the resulting hash as output is identical to the hash you just computed, you can conclude safely with very high probability that indeed this website is trusted because its certificate is valid. Why? Because the certificate authority has attested to the fact that they trust this website. So in short, using some of the same verification techniques that we talked about last time, your browser, unbeknownst to you, and so quickly, as soon as you hit enter on a website whose URL begins with HTTPS, is downloading that server certificate. It's computing a hash to see what it should be. It's then looking at that certificate's digital signature and decrypting it with the same website's public key, the presumption being that it was encrypted with the server's private key, and then that outputs a hash. And actually, sorry, let me fix one thing here. Actually, let's go ahead and do this. Let's go ahead and take a 5-minute break here, folks don't mind, just so I can make sure that we're doing this right. Be back in 5. Apologies. So what happens when you actually visit a website? So one, your browser downloads the server's certificate that it presents as part of that interaction. Two, your browser then runs that certificate through some algorithm that produces a hash value of the certificate based on certain fields within the certificate. So recall that a hash value is a fixed length message that sort of represents on a very smaller... Sorry, let me start that one last time. Sorry, everyone. So what actually happens when your browser visits a website? Well, it first downloads the certificate from that website, assuming you're using HTTPS. Your browser then calculates a hash value for that certificate by looking at certain fields within it using a special hash function that produces a fixed length representation of the certificate. Now, why does it bother doing that? Well, the next step that your browser does is it does this. It takes a look at the signature on that certificate. It uses the certificate authority who signed that certificate's public key, and then it uses that CA's public key, the signature from that server certificate, runs it through this algorithm here, effectively decrypting the signature with the public key, and that should produce the exact same hash value. That is to say, if you visit a server and it's presenting you with a certificate, and it says that that certificate has been digitally signed by a certificate authority, your browser can use the certificate authority's public key to decrypt that signature, and by way of these hashes, confirm or deny that, yes, that server's certificate was indeed signed by the certificate authority. And again, if you trust Google, if you trust Microsoft, Apple, Mozilla, and that's another question all to itself, but if you trust them, and they in turn trust these certificate authorities, the presumption is that you should trust your secure connection with this particular website. Now, with that said, does HTTPS and in turn TLS keep you secure? Mathematically, yes, but you and I as the humans are again the potential weakness here. Why? There's another attack called SSL stripping for historical reasons, but now it refers also to TLS. And what this attack involves is tricking the user into thinking they have a secure connection to a website when they might actually have not an encrypted connection to that website. And worse yet, they might actually have an encrypted connection to a third party, a machine in the middle's own website. So how might this work? Well, if you and I are in the habit of only typing still URLs as http://www.example.com, or maybe you are and are in the habit of just typing www.example.com, enter, into our browsers. Or maybe more likely, you and I are in the habit of just typing example.com, enter, in our browsers. Well, if you watch the URL bar, the address bar in your browser, you've probably noticed over time that even if you type the most succinct of those inputs, it eventually gets converted into a longer URL with the HTTP, maybe with the www, and perhaps even more characters as well. And that's because your browser is just trying to be helpful. Technically, to visit a website, you need to use a URL. And a URL in this case should start with http:// or maybe https://. But your browsers are trying to be helpful, so if you don't even type any of those, it might first try HTTP, and then it might try HTTPS even. But the catch is that if you start your interaction with a web server using HTTP, that alone might be enough of a window of opportunity for an adversary to do something malicious with the packet of information you're sending to the server, and then maybe send you back a response that tricks you into ending up at some other website altogether, or perhaps just the adversary's own website. And they might be super clever and make you think that you have a secure connection to the original website that you visited. So what do I mean by that? If inside of your browser's virtual envelope is an HTTP message like this, which is just saying, get me the home page of example.com. But suppose for the sake of discussion that you are not using HTTPS, you just typed HTTP or nothing at all, and you're trusting your browser to fill this in for you. What might come back from the server? Well, the server could respond with a message that says this, HTTP version 3.307, which is another status code which means redirect the browser to a different URL. This is the browser's way of saying, detour, go to this other URL instead. Well, what location is that URL at? Well, perhaps this one here. But the catch is that if you're using HTTP and therefore your request is unencrypted, and suppose for this story that there is a machine in the middle waiting there, listening to attack you, it could actually be that this response is coming from that machine in the middle and not the actual website that you intended to visit. Why? Because if Alice is trying to reach Bob, but Eve, the eavesdropper, is in the middle, it could actually be Eve in the middle that's responding with this request. So Bob doesn't even know what's going on in this story. But the catch is here, notice that this eavesdropper, this machine in the middle, is particularly clever because they're suggesting that you be redirected per this status code 307 to https://. And odds are you and I are probably in the habit of at least making sure that our browser says secure, or that at least you're at an HTTPS URL. So you might think, whew, good, everything is the way it should be. Now this is very, very subtle, but what if I draw your attention to the actual URL I'm being sent to here? At least on a US English keyboard using this particular font, this is no longer example.com, example.com. This is now indeed examp1e.com. So this is a particularly subtle attack whereby the adversary in this story seems to have bought a domain name that looks very similar to example.com with an L, but they instead use the number 1, which in some fonts and on some screens looks so close to an L that are you or I really going to even notice this difference? The implication, though, of this subtlety is that you might very well have a perfectly encrypted connection using HTTPS to a server, but it's not Bob's server in this story. It's now Eve's server in the middle. So SSL stripping in this case refers to an attack whereby you're sort of stripping out what would be an HTTPS redirection to the right place, and maybe you never even end up at HTTPS, and the eavesdropper in the middle always keeps it as HTTP. But an even more malicious adversary might take it one step further and actually redirect you to their own HTTPS site, at which point you might be vulnerable to the phishing attacks that we've discussed before, where you might provide information into a website that is not actually legitimate. So how can you mitigate this kind of attack? Well, one, if you're a user, a consumer, you could just get into the habit of always typing out HTTPS:/ and then the domain name that you want to visit. I will concede that that can get tedious quickly, but that is hands down the most paranoid solution to implement here, because you know you will end up at HTTPS. Hopefully the website actually supports HTTPS, but most websites nowadays certainly do. With that said, if you're on the flip side of the story and you're actually the designer of the website, the business owner running the website, or you have control over not the browser but the server, there's a few different things that you can do. And in fact, you can use a protocol called HSTS, which is to say you can actually configure your server to provide hints to browsers that, you know what, they should always use HTTPS when talking to the server, no matter what the human has decided. And HSTS here, for Hypertext Secure, Strict Transport Security, has you, as the administrator of the server, just configure your server to send an additional HTTP header. That is to say, an additional line of text inside one of those virtual envelopes that just informs the server that we really want to be strict about our transport security. That is, we want to be using TLS. We want the user to be using HTTPS. And here, the server is telling the browser, assume that this is the case, that I want you to use strict security for at least 1 year. This is the number of seconds in a 365-day year, for instance. That's just a really long time telling the browser that, yes, I'm going to keep my security on for at least a year, which should be the case anyway. But you can further configure your server to not just output this response in every one of those virtual envelopes going back to browsers. You can even more protectively say, use strict security for subdomains as well. So even if my user is at example.com, also make sure that their browser uses HTTPS for something like www.example.com, where in that scenario, www you can think of as a subdomain because it's part of the example.com domain itself. And so what is this telling the browser specifically? Even though you might accidentally, conveniently visit a website for the very first time using http:// because you typed it or you let your browser automatically fill that for you, If the server responds with this message, the whole point of HSTS is that the second time, the third time, the 300th time, the 3000th time that your browser visits that exact same domain in the future, up until at least a year from now, it will automatically switch you to HTTPS. And it very protectively won't even let you visit the HTTP, even if that's what's in the URL bar. It's just going to say, nope, I've been told to use HTTPS instead. And that therefore decreases the window of opportunity for adversaries to just that very first request that you might make accidentally, conveniently, that's using HTTP. But every subsequent request from your browser, according to this model, will now be HTTPS instead. And you can go one step further too. If you're the administrator of a server, you can also include the keyword preload in this message that's inside of all of these virtual envelopes. And what that will further tell the world is that if the browser manufacturers would like to preload this information into Chrome, into other browsers that humans download, you can even eliminate that first window of opportunity, because you can have your domain name included essentially in the source code for browsers like Chrome, so that when people download Chrome itself, visit your website like example.com, your browser will already know that they should not use HTTP with this website. They should use HTTPS. Questions then on HTTP, on TLS, on HSTS? It's a lot of acronyms, but realize that some of these defenses are available to you as a user, and some of you, if more technical, these defenses are available to you as system administrators. Max, over to you.
Hello. So I have a couple of questions. So you mentioned that there is such websites as exam1e.com, and they very similarly look to example.com. And I know that registrars fight against phishing websites like this. And whenever somebody tries to register a domain that's looking a little bit suspicious, it usually marks it as fraud and suspends it. So how do such domains still exist? And why is it so common? And another one that is connected to that, I actually forgot it. OK, that's the only, that's the only question.
That's a really good question. And that's great that registrars, who are the companies in the world that sell you or rent you domain names nowadays, are being more vigilant when it comes to your buying a domain that could be maliciously used in this way, because it's so similar to a brand name or an existing website. However, there's a lot of registrars out there, and I would conjecture that not all of them are as good as others at doing that detection. There are hundreds of top-level domains nowadays, TLDs, which means that you could even choose example.something else potentially, and that too might not be caught in this way. Now, eventually, maybe, especially when you use it maliciously, you would eventually get shut down. But maybe it's enough to attack one person or 2 or 10 or 100 before it's actually shut down. So these remain theoretical and actual attacks, but there are certainly ways to push back on this. A good question. Others from the group? Yuan Ting?
Hello.
Hello.
Hello, David. I would like to know that is HTTP is the best solution for cookies and super cookies to prevent from attack, or should I clear the cookies frequently?
A good question. Unfortunately, super cookies cannot be stopped at the browser level. Super cookies refer to a type of cookie that's embedded by your company, your university, your internet service provider, and you would have to opt out at that level. So for context, for Americans in the group, AT&T and Verizon started doing this a few years ago, where they were injecting cookies into cell phone customers' HTTP requests. You literally and stupidly and obnoxiously have to log into your Verizon.com or your AT&T.com account via the web or the app and opt out of this. So one thing to your question here, super cookies are actually super annoying, super difficult, super dangerous in that sense, because they can happen without your knowing. However, if you are using HTTPS, that should decrease the probability of this happening, because if your data is encrypted, your company, your university, your internet service provider can't insert the cookies into those encrypted messages. unless, and we'll talk a bit about this more later, unless you have given permission to your company or university to install special software on your Mac or PC. So in short, simplest advice is always use HTTPS. And if you have a cell phone provider, Google around, find out if they might be doing this to you. And if so, figure out if you can opt out. How about one more question here? And Matthew, I'm seeing in the chat, is accept all cookies the same? No, completely different. Those are non-super cookies that are in your actual browser. Super cookies are meant to be out of band from like your company or ISP. Matteo?
Yes, David. My question will be like from a macro perspective, will it be feasible in the same way that there are machine in the middle attacks, machine in the middle verifications? Like, you know that a request from, let's say, my cell phone to the Zoom meeting right now needs to do so many hops to reach the server, right?
Mm-hmm.
Will it be appropriate if between each hop every packet will get like a stamp, like a passport to verify the integrity of the connection?
Potentially. The catch is, and if I'm understanding the question correctly, the catch is you, I, we don't control all of these machines in the middle when it comes to routers. So it's possible to do what you're doing, but there just isn't coordination at that level. And so per our discussion last week of end-to-end encryption, in general, it's best that the sender and receiver worry about doing the encryption, because that way you don't have to trust anyone in between you, any machines in the middle, so long as you are using a protocol that supports some form of encryption end-to-end. All right, give me just a moment to reset, and we'll resume with a few more topics and then questions. And Carter, did I speak right? Did I say hypertext strict transport security? You did. OK. Sorry, Mike. Or what, Max? No, that's OK. OK. We just went from questions. So, all right. So how else can you protect your data? Start that over. So how else can you secure your system when intercommunicating with others? Well, you might have heard this term in technology, namely VPN, a virtual private network. So what is this, and how does it relate to something like HTTPS? Well, first of all, HTTPS, to be clear, is only used for the web. HTTP is hypertext markup. Sorry, no, let's do this once more. Sorry, y'all. So how else can you keep your system secure, particularly when they're communicating with others? Well, another technology with which you might already be familiar is this, a VPN, or a virtual private network. Now, whereas HTTPS only secures your web traffic between browser and server, a VPN is, dare say, a more powerful technology because it encrypts all of your internet traffic between you and whatever VPN server to which you're connecting. So how does this work? A VPN allows Alice and Bob to establish an encrypted channel that even if there are machines in the middle, routers or otherwise, that shouldn't matter because Alice and Bob are using cryptography to encrypt all of the information going in between points A and B. Now, how might you use this? Well, it's very common if you work for a company that itself has servers that you might need access to, whether it's email or files or anything else. You might, from your laptop, have to, by policy at that company, connect to your company's servers via VPN, virtual private network. That is to say, your Mac or PC or your phone have special software that you start up. You probably log into using minimally a username and a password, maybe using a two-factor code, maybe using a USB device that you have to connect to your computer. You have to somehow authenticate to that VPN. And once that software is up and running and authenticated against the VPN server run, in this case by your company, all of your internet traffic thereafter should be encrypted between you, point A, and the company, point B. The motivation for that is that this way the company can ensure that no matter what services you are accessing inside of the corporate network, be it email or files or maybe video conferencing or something else altogether, no matter what, by nature of that VPN, all of that traffic is encrypted. But you should realize, too, that VPNs have a few side effects, perhaps good, perhaps bad. When Alice connects to Bob, if Bob is the VPN server, she has this encrypted tunnel. This is what we mean by a virtual private network. She has this encrypted tunnel to Bob, which typically makes it appear as though Alice's IP address, her internet address, her unique identifier on the internet, is actually that of Bob and not her own. That is to say, if Alice connects to her company's VPN server, she then gets another IP address from her company's own VPN server effectively. So if Alice then visits gmail.com or amazon.com or any other website, those websites will actually think that Alice's IP address is that of Bob and not Alice. So this is very commonly used if you're in one country and you want to masquerade as though you're in another. And this might be because you need to in order to access company resources. Perhaps from a show of smiles, this might be because you want to access a streaming media service that you don't have access to when you're in one country or another. The point, though, is that you have this encrypted connection between points A and B, and thereafter, you can visit any website, any service, as though you are physically at location B. Beyond that, there are other technologies that you can use to encrypt communications, and this one's a little more technical and used by programmers and system administrators alike. There's a protocol called SSH for Secure Shell, and this is a technology via which you don't necessarily encrypt all of your traffic between point A and B, although you can use SSH to create the equivalent of a virtual private network or VPN. But SSH is all about connecting to a remote server and executing commands on it. So not executing commands on your own machine ultimately, but on some other machine that's maybe inside of your company, your university, or somewhere else in the world. So for instance, if curious as to how this works, you might recall that in a previous class I wrote some code on my computer, and then I opened up a terminal window that started with this prompt, a $sign. It doesn't mean currency. It's just a tradition that the $sign means type your commands here. But at the time, I was typing them on my laptop here on a local server, if you will. If I, though, want to use a computer to remotely connect to another and then remotely run a command, it might work like this. Here I am, let's pretend on my own computer, and suppose I type out one command like the date command. If not surprisingly, this will tell me what the current date is. So suppose that where I am on my own computer, it is Thursday, January 1st at midnight Eastern Time in the year 1970, for instance. If, though, the next command I run is not date again, but I use SSH, and I connect, for instance, to, how about our friends at Stanford University? So I'm going to SSH into stanford.edu's server. As soon as I'm at that server now, I get another prompt in this case. But if I now run the date command, what you'll see is that the date is now apparently slightly in the past, at least if I type this quick enough so that the seconds weren't off. Wednesday, December 31st, 9 p.m. Pacific time in the year still 1969. So this is to say SSH is actually a very common technology used in the world of software engineering, system administration, when you want to control one server from another. And what's powerful about it is that everything I just typed after that SSH command, even as innocuous as the date command is on Stanford server, would be encrypted. So no one between these points A and B would be able to know what I'm controlling or what commands I have typed. Questions now on VPNs or SSH itself? Yeah, Saeed?
Hello, sir.
Hello?
So I have 8 questions. So first one is, if someone get our IP address, so then the other person can get access into our system. And the other question is, the second one is, how port forwarding actually work, and what is the difference between sub-cookies and cookies?
OK, so 3 questions. We will get to the port forwarding or ports in general in a moment. Cookies are pieces of information put on your computer by a web server directly, like when you log into a website. A super cookie is a cookie that isn't even put on your computer. It is put into the virtual envelopes that your computer is sending to servers. And your internet service provider or company might do that on your behalf. And the first question, I'm sorry, Saeed, I didn't quite get it. If you don't mind typing that one into the chat, maybe Carter can help with the very first, which I missed. Mohammed asks in the chat, so David, do you think all cookies are dangerous? Short answer, no. Like, cookies are, as a technical person, a wonderful feature of the protocol HTTP because they enable browsers to maintain state with servers. Like, that is a very good engineering problem to solve. The problem is that in the real world, humans have used them maliciously or irresponsibly or annoyingly for advertising, for tracking, and ways that they were perhaps not intended, but that is a logical outcome of their existence. More on this in our final lecture on privacy, but increasingly companies like Apple and now even Google are making it harder for cookies to be abused in this way. And this is why companies like Facebook or Meta are so upset with these changes, because they impede advertising. But more on that another time. Last question here by Mahal.
So my question is, what does antivirus or ad blocker software actually do to prevent these things from popping up?
A really good question. We will cover that today, and they don't solve any of the problems we've talked about yet. New problems that we're about to see. So a good question. All right, give me just one moment here. And Carter, we might want to just cut this demo as being fun but off topic. All right. Maybe, yeah. Let's do this all. We're doing well on time. We're going to change topics here in a moment. So let me go ahead and on camera say, all right, let's go ahead and take a 5-minute break. And when we resume, we'll look at some other building blocks of systems that both solve problems but also create vulnerabilities for us as well. Back in a few. OK, we'll be back in 5 minutes. 5 minutes. All right, so let's talk about now what's actually been on the outside of these virtual envelopes that's helping these envelopes get from their source to their destination. So it turns out that on the outside of these envelopes, minimally, is what we'll call a port number, which is literally just a unique number that the world has decided on that uniquely represents the type of service that that envelope is destined for. So for instance, if you at your browser were going to pull up a website like http://www.example.com, on the outside of that envelope would not only be some mention of www.example.com, but also a so-called port number, namely 80 by convention, which means that this envelope should be opened not by the other server's email server or chat server, but by its web server specifically. Now, if the web server were to respond to us by saying, we want you to use HTTPS instead, essentially redirecting the browser to a secure version of the website, my browser would then have to send a second request to the server, this time still mentioning www.example.com, but on the outside of that envelope, among other details, would be a different port number, namely 443. Now, these aren't the kinds of things you have to memorize, but the computers certainly know what they represent. And in fact, common numbers include 80 for HTTP, 443 for HTTPS, 22 for SSH, and hundreds, if not thousands, of other numbers as well that humans decided on, but the computers actually rely on to know what piece of software on a computer should actually expect and open up these virtual envelopes, these things we've called packets. So what's the problem or danger here? Well, it turns out that your computer can be listening for internet traffic on none of these ports, in which case it's completely disconnected from inbound connections. But very often computers, especially servers, are listening, so to speak, for envelopes destined for maybe port 22, maybe port 80, maybe port 443, maybe others as well. So you might think, well, that's not great, because if these numbers are standardized, then adversaries could maybe try to access my server via those port numbers because they too know what they are. So you might think, all right, well, let me run my web server on a number other than 80 or a number other than 443 and just choose a random number between like 0 and 65,000 or so, because the odds that the adversary is going to guess that are much lower. SSH, you might consider doing the same. But unfortunately, it's all too easy for adversaries to wage this kind of attack known as port scanning. And recall that we did our own brute force attack in classes past on our own passwords, for instance, trying to figure out all possible passwords that might be locking a phone. And it's not that hard to use code very much like that with a loop of some sort that just tries every possible port number between some range, roughly 0 to 65,000. So port scanning refers to the equivalent of knocking on the door of every possible port number on a server. Now, most of those doors might be closed and no one might be home. That is, they might not be expecting any traffic or visitors on those numbers. But by writing software that tries all of those port numbers, you can essentially discover services that are running on certain computers. Now, hopefully that in and of itself is not a problem, because most likely the purpose of these services is to be on the internet. But hopefully these services, too, are using encryption. Hopefully they're using authentication. But that's not always the case. So security through obscurity, so to speak, running services on random or arbitrary non-standard port numbers is not really a good practice unless you're additionally defending against all of these common attacks. Now, in the world of port scanning, though, it's a specific example of what we might call penetration testing more generally. Penetration testing, or pen testing, is actually a skill, a technique, a job even, whereby you are hopefully not an adversary, but hopefully a well-paid consultant whose purpose in life, or whose vocation in life, is to actually try to penetrate someone's network or penetrate someone's system. And what do I mean by that? Well, maybe quite simply, you try scanning all of the ports on their servers just to see if there are ports that are open, that is listening, that shouldn't be, because no sense in opening a door if no one's meant to go through it. Or you might try to penetrate their network or system in some other way. Maybe you might try to brute force your way through passwords. Maybe you might try to socially engineer the employees of that company or the like. So penetration testing is all about someone who, for good purposes, is trying to find possible weaknesses in your infrastructure so that hopefully you can pay them and thank them, but then fix those problems before actual adversaries try to exploit it for malicious purposes instead. So this might also be referred to as ethical hacking, where you get all of the cachet of being a hacker and really good with computers, but the upside of doing it ethically, which is to say that if you are in the business of trying to find faults with systems, you don't have to do it for illegal financial gain, but for very much legal financial gain instead, as in someone will pay you to find faults in their system so long as you tell them and only them first so that they can actually fix the same. And in fact, in this world, there's a gamification of it of sorts in certain companies where you might have a red team whose purpose in life in this game is to actually try to penetrate the network or find some faults, and then the blue team, so to speak, whose purpose in life in the story is to defend the systems against those attacks. And so that too has often yielded better results for some folks, given that it helps them find weaknesses before adversaries who don't work for them do. So how might you keep these attacks out? And how might you keep even penetration testing out in a good way to demonstrate that, you know what, we are actually pretty secure? Well, there's this technology with which you might be generally familiar by name, namely a firewall, which actually comes from the real world. Typically in buildings that might have multiple stores, there might literally be a firewall between two of the stores so that if there's a fire in one store, it doesn't somehow propagate next door to the other store. Now, in the virtual world, a firewall is essentially a piece of software between you and the outside world, or between you and some other network that keeps data in the network that you don't want to leave it, and it keeps out from the network data that you don't want coming in. So for instance, if you might within your company or university or home have some sort of local chat service or intercom system or the like, none of that traffic ideally should end up on the public internet. So you might want your firewall to block any intentional or accidental attempts to transmit that data outside the network. Conversely, if you have a private network that you only use for home computing and watching streaming media and the like, you are not yourself a server, and you certainly don't want random on the people trying to connect to your laptops or desktops or servers in your home. You might want your firewall to keep all internet traffic out. Now, with that said, there are some problems when you want to use services where you do need to talk to someone on the outside world, maybe like a Zoom call or the like, but there are technologies that help mitigate this, so these firewalls are not necessarily absolute. You can open them up or poke holes in them, so to speak, to allow certain services through. So how might these firewalls actually work? Well, they might simply block traffic, that is, internet packets, based on IP address. Because recall, on the outside of those virtual envelopes is not just port numbers, but also, and not quite the domain name like www.example.com, on the outside of those envelopes is actually the unique address of a server to which you're sending a packet, and the unique address of a client that is expecting some response there too. So an IP address is just a numeric, unique address for, let's say, every computer on the internet. It's a bit of a simplification, but it's very similar to the postal addresses that you and I use to send mail, old school style, or postcards throughout the postal system as well. So you could quite simply, if you as a parent, for instance, don't want your kids accessing social media within the home, you could just configure your home's firewall to prevent access to the IP addresses of known social media sites. And so if the kids are trying to use the laptops or desktops in the home to connect to those IP addresses, it would effectively be blocked and not allowed through, so long as the software in question, the firewall, knows or can figure out what those IP addresses are. Now, that said, it's not fail-proof. All it takes is for someone in the home to have some out-of-band device, like a cell phone, that uses the mobile phone network. And then, of course, you circumvent the firewall that might be based only on your home network. So you have to keep in mind exactly what it is you are firewalling and which networks they're in. But IP address might not be quite all that you want. You might want to deny access to certain services altogether by way of, now, you might not want to block access to sites based solely on their IP address, but perhaps based on those port numbers. So for instance, if you wanted to block all internet traffic in or out of a network, you could just use your firewall to block all of those port numbers. But if, wait a minute, you realize that you still want to be able to remotely control a computer or server in that network, you could open up just one port number, for instance, 22, if you want to allow SSH back and forth, or whatever port number your preferred VPN software uses instead. So you can use firewalls to block traffic based on IP address, based on port number, or even more sophisticatedly via deep packet inspection, which is a big way of saying that even the most sophisticated of firewalls can actually open up, theoretically, these virtual envelopes and see what's actually inside them. And this way you can even more reliably block certain sites by their domain name, not just their IP address, but by their name. You could, for instance, via deep packet inspection, keep an eye out as to who is emailing whom. For instance, corporations that are very concerned about their intellectual property, ideas and products that they have internally, they might use deep packet inspection to make sure that you and I are not emailing the press about some new product under development, or emailing the competition or anyone in the outside world about some product, because via deep packet inspection, you can pretty much look at everything inside of this envelope, be it the sender, the receiver, the contents of the message. But you can also use this too, not just for confidentiality and the like, but also, for instance, to check for malware and malicious software. That is to say, maybe attachments that you don't want to allow through. And we'll consider exactly what those threats might be in just a moment as well. Now, how might a company, a university, or even a home implement this kind of firewalling, or more deeply, this deep packet inspection? Well, we're essentially describing a technology that you would call a proxy. And a proxy is very often a server, though it doesn't have to be an actual physical server. It can be a piece of software running in your network. A proxy is a device that essentially implements a potential machine in the middle attack. But it's not quite an attack in this way. It's by design. A proxy is a device, a server, or a piece of software that sits between two other points. So in this case, Alice might be someone on the inside of a network. Bob might be someone on the outside of a network. And Eve, in this case, is eavesdropping literally because her role in this story is to be that of a proxy. And the proxy takes data from one side and ideally maybe hands it out to the other. But this proxy might indeed be eavesdropping, might be a little nosy. And so as a packet comes in this way from Alice, might look in the packet and decide, we're not going to send this to Bob, and then it might just be dropped or effectively deleted. So companies, universities, even home networks can use proxies to decide yes or no whether or not to allow certain traffic through. So in that sense, they're very similar to a firewall. But sometimes proxies are something that have to be configured even for your own devices, because there might be only one path out of a company network, only one path out of a university. But the catch here is that literally all of that traffic by design now is going through this middle point. And here's where things can get troubling, especially if you do attend a university or you do work for a company where they may be issued your laptop or desktop or phone. So if your company or your school has given you a laptop or desktop or phone, that might be nice that this is one of the perks to have this hardware. But if they have pre-configured it with software, realize that there are implications of that. You might have your own username and password on that laptop or desktop or phone, but they might have installed administratively, with root access, so to speak, some kind of software that could actually be monitoring everything you're doing on that computer. And this is not uncommon in the corporate workplace. But they can also do things more technically. Like they could install their own certificate authority on your laptop or desktop or phone, essentially adding to the list of certificate authorities that Microsoft and Google and Apple and Mozilla have baked into their own browsers. The implication of this is that even if you think that you as Alice can securely communicate with Bob, and maybe Bob in this story is gmail.com or amazon.com or facebook.com. Even if you think that Alice and Bob Alice, can communicate securely with Bob and establish a connection between https://gmail.com. If your browser that is your phone or laptop or desktop, has a certificate installed by your company or university that's acting as a CA, or certificate authority, essentially your computer could be tricked into thinking that you're connecting to the real gmail.com, but you're actually connecting to the company's proxy server. But because you have this additional certificate on your computer, even though the company is masquerading, pretending to be gmail.com, you're actually connected to their proxy server. And they might actually be forwarding your traffic somewhere else, but this is a definition of a machine in the middle attack, but it's facilitated by someone else having used our technologies that we talked about earlier to trick, really, your local device into thinking that this is the real gmail.com, whereas the math might actually be based on the company certificate, not on Gmail's own. So be mindful of that again whenever you're using a device that has left your control or has not always been under your control, that you do not necessarily know what is installed on it. So how else might a company, a university, be observing or keeping an eye out, either for good or evil purposes? Well, they actually might also be doing something that we might call URL rewriting. So if you have a company or school email address via which you receive mails from the outside world, you might notice that whenever an email contains a link, if you hover over the link and look in like the bottom corner of your browser, it might actually not go to the actual link destination that you think it does. It might actually go to a URL like this, maybe https://example.com URL equals something. And the implication of this here is that what companies and schools might do to combat malware, maybe malicious software that could be accidentally installed or sent your way via URLs, or to prevent you from accessing phishing websites that are trying to steal your or the company or the school's information, they might automatically, through some kind of proxy server, acting in this case on email, change every URL in an email you receive to be example.com, and then embed at the end of that example.com URL the actual URL so that you can still reach your destination. But the implication of this is that if you click on this link here, you're first going to visit example.com. That's going to include some data from that proxy server that has added URL equals something, where something might be gmail.com, amazon.com, whatever the actual URL is. But because the company or the school in the story controls example.com, they know what URL you're trying to visit. Now, one, they could minimally just log that information and know that, oh, David seems to be visiting Gmail again. Or they could actually check in their database, is gmail.com or whatever this URL is known to be malicious? Is it known to be a phishing website? And they can just prevent you from accessing it altogether. So this is another form of proxying that's actually very explicit, because you're embedding the machine in the middle quite literally as example.com or whatever your university or your company's domain name is. But it's all toward an end of trying to help protect you from potentially malicious phishing type websites. But the implication too is that now the company, the school, the machine in the middle knows every link you're clicking on as well. Let me pause here and see if there are now any questions about these techniques of proxying or inspecting the packets going back and forth. Sabir?
Hello, David.
Hello.
My question related to VPN, like my question is that when we are accessing the internet with the help of our office or university network with a particular username and password, and if we are using VPN that time, can the office or university know that what we are doing in the internet?
Good question. So if I heard you correctly, if you're using a VPN from a university campus, can like the administrators know what you're using the VPN for? Theoretically, no. They can only know that you are using a VPN, and they can know where you're connecting to, whether it's some company or some other country or the like. However, if they have not installed any special software on your computer, and you're not infected with some malicious software, they should not be able to tell what you are using that VPN for, because everything will appear to be completely random or scrambled within that connection. That said, and we'll talk about this more in our final lecture, you have to realize that when you do things on the internet and in a network, that information alone, that you, Samir, are using a VPN and you are connecting to this endpoint, might be enough information to trace something back to you. So case in point, long story short, there was an example here at Harvard years ago where a bomb threat was actually called in, and it was traced to an email that had been sent by someone on campus. They had used special software at the time to cover their tracks. It wasn't a VPN. It was an anonymization piece of software that we'll actually talk about in a couple of weeks' time. But the catch there, logically, was that they happened to be the only one on campus at that hour on that day using that type of software. And so logically, they were able to conclude who was it that sent that email, even though they didn't see the contents of the email. They didn't see the actual internet traffic. So realize there are these out-of-band detection techniques that derive from really these first principles, like how these systems work. So keep that in mind, too. And this was all public at the time a few years back. Other questions? Raymond.
Right. Thank you so much. So my question is that I just want to know what's the difference between VPN and also Tor network in a higher level, like, just the difference. Because what I do know is that these two networks are used to encrypt or anonymize our activity or the data that we're sending. The second question is that, let's say that I'm using a network at a university or a company, and they also have their own CA, which means that they've got their own databases, like which websites I can get in and which websites I cannot get into. If I'm using VPN, does that mean that the university or the company know what I'm doing?
Good question. So Tor is the anonymization software I was alluding to a moment ago in my previous answer, and we'll talk about that in our final lecture. Tor really is about privacy preserving. So it's about covering your tracks so that, kind of like the Hollywood movies, when you're here, your data is bouncing sort of across all of these different servers in the world, and it's sort of difficult to trace it back to its origins by design. So more on that in a couple of weeks' time. VPN is an encrypted connection just between one point A and another point B. So even though they can't see what you are doing, it is very obvious where your data is coming from thereafter. So legally, for instance, if the VPN server or company were to be subpoenaed, they might have to disclose information about you. And so it's not quite as privacy preserving. It secures your data, but it doesn't preserve your privacy in the same way. On your other question about what you're doing, especially when you're on a VPN, if someone has installed with administrative privileges software on your computer, like, all bets are off. You cannot trust the device. So if they've installed their own certificate on your computer or a CA to the list of trusted things, anytime you use that browser, for instance, like, you are vulnerable to a machine in the middle attack, or at least a proxying type implication. Beyond that, but honestly, at that point, if they've installed special software on your computer, they could be monitoring everything you do on the internet anyway. So sort of all bets are off, unfortunately. OK, one final question before we resume with a final few topics. And then we'll do questions at the end again. Yeah, over to Matteo.
My question will be, I've read about proxies, and I'm not clear about what is a reverse proxy versus a regular proxy.
Sure. So a proxy,
how would it work?
A proxy is as we defined. So if you have a machine between points A and B, a proxy just helps the data get from point A to point B. And its purpose in life might be, one, just a very well-defined point through which all company data has to flow. Or two, it might be a little more nosily looking at the traffic that's going through it. A reverse proxy tends to happen more on the server side. So CS50 uses reverse proxies all the time. So if you have taken some of CS50's own classes and you've gone to a URL like cs50.dev or time.cs50.io, we actually have reverse proxies set up so that when you're visiting cs50.dev or time.cs50.io, you think it is just one server, but it's actually not. It's being reverse proxied to multiple other servers behind the scenes. So forward proxies and reverse proxies, I mean, literally just refer to the direction. The data going out from you or into us is essentially the model. All right, let me just reset and a few final topics before We break for questions finally. All right. So what is it we're trying to keep ultimately out of our systems? Well, I dare say malware is perhaps one of the biggest threats. So malware or malicious software is just software that someone has written that can do malicious things. And that's sort of the nature of software. If you've never programmed before, it turns out that it's not that hard to write a program that if you run it, like deletes all of the files on your computer, or maybe starts sending out spam, or maybe starts mining Bitcoin or anything else. Like software can do anything, and whether it's malicious or not is really up to the human who wrote it or the person who's using it. Now, you might have heard of specific types of malware, for instance, a virus. A virus is a piece of software that attaches itself to a host, just like in the human physiological world. The catch with a virus in the digital world is that you, the human, usually have to do something to get infected. You have to open a file that's infected with the virus and start running it on your computer and loading it into your computer's memory and CPU or brain. You have to click on an attachment in an email that's perhaps infected. So viruses generally require human intervention and really human mistakes. You're exposing yourself unintentionally to a piece of software that can now do anything. And a virus can literally do anything that a piece of software can. So it can delete all the files on your hard drive. It can send spam. It can start Bitcoin mining. It can email all of your files to an adversary. Like once you have a piece of software running on your computer, all bets are off. So you might wonder then, well, what's the line between a virus and like Microsoft Word or some Spotify or some other piece of software you install on your computer? I mean, really, it's ethics at the end of the day. We are trusting that Microsoft Word and Spotify and other software you might install on your Mac, your PC, or your phone just isn't doing bad things. Because very often, once you have a piece of software on your computer, it technically can do anything that the operating system, Windows or Mac OS or iOS or Android, make possible, thanks to those manufacturers. And it really is a code of ethics. It really is perhaps capitalistic pressures that ensure that companies aren't necessarily infecting us with software that's doing bad things. Why? Probably bad for business, if nothing else, if they're caught doing something malicious. But with that said, for historically, it's quite possible for software to be written, even within the constraints of an operating system, that does bad things. And heck, maybe it's even accidental. It has absolutely been the case that sometimes software deletes things that it shouldn't because some human made a mistake. Now, with that said, gradually the world is getting better at designing better and better operating systems that try to sandbox things. And iOS, which runs on iPhones and iPads and the like, is actually particularly good at this, whereby sometimes annoyingly, apps can't do something without your explicit permission. Now, you and I might not give much thought to just saying, OK, 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 because we want the software to do its thing. But more so than operating systems past, you and I are increasingly being allowed to weigh in on whether some piece of software can use the network, can turn on the camera, can turn on the microphone. So thankfully, we're getting more and more building blocks to mitigate some of these concerns. But there are still viruses in the world, and you can be infected by them, whether it is some file you've downloaded and run or some email attachment you've clicked. But more worrisome is another type of malware that we might call a worm. And a worm is very similar in spirit to a virus in that it's just malicious software. It can do anything. But these things can travel from computer to computer even without interaction by humans. Now, how do these work? Well, let's do that again. Now, how do these work? Well, a worm, once infecting one computer, theoretically can start Let me fix this once more. Sorry. Now, how does this work? Well, a worm theoretically, once it's installed on one computer, having infected it and running, well, it could do that technique called port scanning from earlier. And maybe it can use that infected computer's internet connection and just start scanning the local network or a broader network for IP addresses of other computers and ports of other computers. And if one of those computers' ports happens to be listening, and for unfortunate reasons, that computer is not using encryption, it's not using authentication, and it's vulnerable somehow, theoretically, that worm can travel from computer to computer to computer by making these network connections via these ports at these IP addresses. And that is quite often how they have spread. It's the result of mistakes in software. It's the result of there having been holes in our firewalls, in our systems, by allowing them through via these techniques. So what's the downside really? Well, beyond just wreaking havoc on your own computer by deleting all of your files, spamming people, Bitcoin mining, and the like, actually what adversaries have increasingly been doing over the years is creating botnets, so to speak. That is, it turns out it's more valuable to an adversary not to completely disable your system, because that doesn't really serve them long term, but maybe to install software on your computer that's just constantly running. And it's not actually doing anything bad to you. None of your files are deleted, no spam is being sent, but you are infected. And there's just some piece of software constantly running on your computer. But maybe this adversary has somehow figured out how to infect not just your computer, but my computer and your computer and your computer and your computer and hundreds, thousands of other computers in the world. Now, if this software is smart and it's constantly listening for commands, an attacker can send some kind of command, not unlike those virtual envelopes, to this entire botnet of computers and say, OK, computers, now everyone at the same moment start attacking some server. Or everyone at this moment start sending emails. Everyone at this moment start mining Bitcoin. And so you can leverage the network of hundreds or thousands of computers all at once and have a much more powerful attack therefore possible. And what form do those attacks take? Well, quite often what we'd call a denial of service attack, or DOS. And this is exactly as the name suggests. Sometimes adversaries' goal in life is just to deny service to everyone else, whether it's for political reasons, financial reasons, or the like. It's one thing for me on my laptop or my phone to maybe visit, maybe I'm a little annoyed at Google today. So I go to google.com, and then I keep hitting reload, 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 or faster, reload, 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 reload. I'm trying to deny service to other people, but realistically, Google has way more resources than me. So a denial of service attack only really works if you have a lot of resources yourself, more resources than the site you're attacking. But with botnets, when you control multiple computers, you can actually wage a distributed denial of service attack, whereby, again, you send a command to this whole network of infected computers, and you say, all right, everyone, go visit google.com right now and reload, reload, reload. And when it's hundreds or thousands of computers doing it to Google, or maybe not someone as big as Google, but maybe a small business that they're annoyed at or they're competing with, you can, via distributed network, try to deny service to actual customers or users of that site. Why? Well, a computer, long story short, only has so much memory, only can do so much per unit of time. And if you completely distract a computer or server by all of these requests that are sort of bogus, then the good requests from the real users, the real customers, can't necessarily squeeze in. And so you're denying service to other people. And distributed is particularly malicious. Why? Well, once a company figures out what's happening, like Google, they could just block with their firewall my IP address, for instance, coming from my phone or my laptop or other device. Once they know where the attack is coming from, they can just deny, or they can block service there. But if it's distributed, if it's coming from all of us or thousands of people, thousands of IP addresses, then it gets a little harder. Like, technically, they could just block all of our IP addresses, thousands of IPs. But very often, you and I share IP addresses if we're on the same campus, on the same corporate network. Even though locally we might have unique addresses, to the outside world, we might all share one public address from our whole company or school. And at some point, it's not going to be in Google's best interest in this story to block all of those IP addresses, because then we might be denying service to actual good people on this campus at this company who just happen to be on the same network as this attacker or as this infected computer. And so that's really the value of attacking computers nowadays. It's not just one thing to get at your computer individually. It's what your computer represents. You are a node, a potential ally on a network of systems. So it's just as well that we try to keep this kind of software out altogether instead. So how? How do you keep it out? Well, for years, you've probably heard about, maybe you've been using antivirus software, and that's exactly what it does. Antivirus software is software you either download for free, maybe pay for, install on your computer, and it's generally constantly running. Or maybe it runs on a schedule to check, are there any known viruses or worms on this computer? And if so, let's delete them, or let's somehow remove them safely. And maybe you have to reboot to get them out of memory, but then maybe you're back in business. To be fair, that might be too late, because the emails, the spam might have been sent, the files might have been deleted, but it at least gets it out of there for the future time at least. But there's a problem with antivirus software alone in that it has to actually be current for the attacks that you're facing. That is to say, the antivirus software to work has to know about the virus, has to know about the worm. Now, how can you make sure you're always current? Well, you can enable automatic updates with your antivirus software or even your operating system more generally. And in recent years, the world has kind of realized that even though there are downsides of automatic updates, it's generally proving to be, it seems, a net positive for society. Why? Because it ensures that you and I and everyone else are generally running the latest versions of software, which generally means we've fixed security holes, that is, security-related bugs in previous versions, so that at least we're not vulnerable to yesterday's mistakes. You know, we're still vulnerable to today's and tomorrow's mistakes when people continue to write software that's buggy, but at least we're staying current. This also ensures, too, that companies can focus their resources generally on the newest versions of software, and they don't have to worry about being backwards compatible and spending time and effort and distraction on software that might be older and older and older. So enabling automatic updates is generally proving to be a good thing, I dare say. But there are downsides. You know, Google, Microsoft, Apple, and others, they're not perfect. And it has definitely been the case that they or companies have released an update that actually breaks your computer or mine in the sense that now I can't access it or something went wrong. And so generally, automatic updates are not something you do to all of your customers all at once, but maybe a few, then a few more, and just to make sure that we're not going to break or brick a whole lot of our users' computers. But generally speaking, turning on automatic updates will at least ensure that you're not vulnerable to problems the world has already solved. And this is a good thing because there's nothing worse than realizing, oh, I've been attacked and there was something you could do about it. You could have updated your software already. But the catch is that there are also these attacks known as zero-day attacks. And the problem with antivirus software in general, and even automatic updates, is that there's still humans involved in this process, whereby they have to realize, ooh, there's a new virus in the world. Ooh, there's a new worm in the world. Ooh, we made a mistake. You have to fix it. You have to update the antivirus software to detect those new threats or those new viruses, those new worms. So a zero-day attack is an example of attack where an adversary maybe writes their own virus, their own worm, gets it out into the wild, maybe on enough computers that they can do something particularly destructive or valuable for them with it, and the world just doesn't have time to catch up. So even if you have antivirus software installed, automatic updates, it might still take a day, a week for the companies who design that software to update those products for you. So even then, you're still vulnerable. And that's why security really is going to be this multi-pronged approach, especially when it comes to our systems. It's not enough to just use antivirus software. It's not enough just to have a good password. It really is a layered defense so that you create this gauntlet of defenses ultimately that adversaries have to get through. And if they get through one, hopefully you're fine. If they get through two, hopefully you're still fine. If they get through three, maybe then you should start worrying. But security really isn't this absolute. Recall from where we began, we really just want to raise the bar, raise the cost, raise the risk to the adversary so that, again, they hopefully lose interest in little old me. So that's it for today's focus on systems. Hereafter, we'll focus on software, specifically on what you can do, whether you use or write software. And thereafter, we'll take a turn to privacy as well. All that next time. OK. And thank you all so much for joining. The team and I are just going to debrief down here. Let me do a couple of questions on camera here. Then if Carter doesn't mind stepping out, we'll do some Q&A as well. And our next lecture is not next week. It will be in 8 days. Well, 7 days from now instead. Question from Natalie.
Hi.
Hello.